Welcome to another problem session. So today I have another problem that has an application of a Faraday law. There is a very long solenoid and its current enters and then kind of loops and goes and exits somewhere. Maybe current just somewhere current just comes out and goes like that. So this is a structure, and inside there is a metal ring, say A, B, C, D, and it's oriented so that the axis of, in the direction in which the magnetic field is, and the normal is has a angle theta if the normal is in that direction. If the normal in the other direction, then it's like 180 degree. This will be 180 degrees minus theta. So depending on the normal, it will be one of the other angle with respect to the axis. Okay, the current in this solenoid is varied with this kind of profile, and a formula for that profile will be something like it's increasing over here, and it will saturate to I0 if it allowed to continue. But at time ta, it kind of turns off, and it is decaying up. Current is decaying in there, but the direction is still the same. Okay, current is still positive and it's still the same direction. And because I didn't go all the way to the saturation, this some current I1, and so I1 I0 will be related this way. Why? Because I just set this figure out. This is I at t equals to ta. So you can see t equals to ta, this goes to 0, and you get this as an answer. Okay, so this is a constant value because tau is a time constant, which is in a circuit like this. When you turn the switch on, because of self-inductance and all, the current takes time to get to some saturation. Okay, so this is a problem in which there will be induced current because the flux through this will be changing, and during the time the flux is changing, it's actually all the time the flux is changing, and so there will be some induced current. But induced current will have different direction, you will see. Okay, so if you know how to do this, you can find the magnitude, and the direction is very, very tricky here, and you can get the direction using Lenz's law, or you can get the direction using the analytic form of the Faraday law, and try to do this problem on your own and come back and see how I do it using analytic form of the Faraday law. Okay, so let's how I do it. So Faraday law, remember Faraday law is EMF minus of EMF is equal to this E dot dl integral, which is pick a direction in this a loop in space, is equal to minus d by dt of this expression over the area of the loop I pick over the surface, b dot n hat dA. But if this dA is not going to change in space, it's not area of the loop is not stretching or contracting, then you can take this integral inside, and as is the case here, so here this will just become minus dv dot n hat dt dA. So usually this is most of the problems you're going to end up with like this. Only in some problems the dA changes, like when we have a railgun problem, then this area itself is kind of getting bigger and bigger. So that's kind of problem you can't do this. So in that kind of problem, we look at limit minus, and there are other videos that illustrates that. So you can evaluate this as t plus delta t, and take the same thing, evaluated t divided by delta t, and delta t goes to 0. So you can think of this whole thing as in this way, and so this kind of problem lends itself like that. But the problem here is area is constant and fixed amount of area, and in that case you can just take the ddt and bring it inside, and it's convenient here. So to get the current, all I have to do is current will induced will be simply EMF. So this is induced EMF is called, over R. I put absolute value because I don't want to get the direction. So the direction, for direction you can do Lenz's law, which is a little bit hard in some cases. I try to figure out if this is positive or negative when I'm done with, when I do this integral, is it positive or negative. So if E dot dl is greater than 0, then whichever dl, so then we say E is parallel to dl, and E is the direction in which the current will flow. Current will be parallel in the direction of dl. So that's one way. Another is if this was negative, if E dot dl integral gave me negative, then E will be opposite to dl. So whatever the direction I picked for the dl, and this is the direction for the I, so I will be opposite to dl. I will be opposite to dl. So that's the another way to get, and we're going to just follow this, okay? Here, because this analytic expression here is pretty hard to do, flux increasing, decreasing, and things like that. All right. Yeah, I just when I was erasing this, I just forgot, and I recorded the entire thing here, and then I realized the whole thing was on pause. So let me go over one more time. So we're trying to compute this quantity here, this quantity here. Now B is along the axis, and this is because of the infinite solenoid. We can write magnetic field that way. Now for n hat, we pick a direction for dl. So that's, say this is the direction for dl. So it's going this way. So we have picked a direction for dl in my little loop over there, this way. So over here is dl this way, over here the dl is that way, over here the dl is that way. So the dl is changing, but I'm just showing one place. So the loop, the orientation is this way, and so the n hat will be 90 degrees right hand rule. So it's that direction. So that I can use this cosine theta. So B dot n hat is just going to be this times I, and I take a d dt of that, and so d dt will just end up with I. And I is just an analytic expression like this, so we just do a derivative, and you can see that because of this minus will come down and kill this minus, that will become a positive here, but this, when this minus comes down, you get a negative here. So for t less than ta and t greater than ta, you have a different formula. So there are two functions here, one function with two domains, right? As over here, from here to here, there's one kind of situation, and from here onwards there's another situation. Okay, so now I can see that if I want to do this, use this inside there, this expression, whether this expression over here does not have anything that depends on dA, because suppose dA was like this. So I had x axis this way, y axis that way, and n hat was that way. That's the z axis. Then element will be, say, dx dy. That will be dA. And all of this whole thing is same for all the elements. So this whole thing can come outside. And as a result, the integral is very easy to do. That's this times the total area. So I got this times the area is just multiply this whole thing just by the area. That's why I got the integral. And the induced current will be, so this is, I found minus EMF. So this minus can just cancel this guy and divide by the resistance of the loop. So this will be my magnitude of the current. That's why I'm going to write absolute value. This is the induced current in the loop, not the current that's going in the solenoid. Okay, the current that's going in the solenoid has IT, which is like, or has this constant I0 and I1 like this. So this is now I want to know which way the current will go. Will the current go in the same direction as I choose the loop, or is it going to go in the opposite direction? Well, that depends on which way the electric field is. So EMF induced, if you look at this over here, this side is positive, and then there's a negative for t less than TA and t greater than TA. So when you multiply this minus is going to cancel with minus, so the EMF is going to be this times this stuff. EMF this times this stuff for t less than TA, that's going to be positive, and EMF will be negative for t greater than TA because of this multiplied with that. So I have positive and negative. When EMF is so E dot dl is minus of EMF. So in this particular case, the E dot dl will be negative, opposite of that, and positive, opposite of that in the two. And so it should be, now the electric field is opposite to dl, and dl was picked this way, then electric field is in opposite direction, means current, induced current is going this way. Let's make sure over here the current is increasing, so flux is increasing. That means in using Lenz's law now, I want to check using Lenz's law. So I would have in the t less than equal to TA time, I will have something like this. This is increasing. That means we want, you might know that want be induced want this way, which means the current has to be that way. I induced has to be that way. Use right hand rule, and so this is the correct orientation for t less than TA. Now, if you do the situation that's after TA, if you look at the time after TA, it's going to be exactly opposite. Okay, so sorry that I didn't really write this, and as I was, that's my style, develop it slowly. I kind of forgot to turn on the restart the video, but I had to re-record the whole thing. All right, this is the answer. Now just a reminder that if you haven't subscribed, please subscribe to this channel so that you can get reminders, and it helps the channel to grow and help other students to discover this channel and learn from it. If you like this kind of explanation and these kinds of problems, I'm posting one a day approximately. I would appreciate if you can hit a like button. So that also helps actually, distribute the channel. If you like this kind of problems and more answers, etc., you want to study on your own, you can go to this website, and there is a whole lot of other problems already solved. It's not video, just problems solved and theory explained in a more direct way. That's it for now. Take care. Bye.